at DeepMind, the type of AI we work on is this neuroscience-inspired AI, so inspired by how the brain works at a very high level, a systems level. So one way we articulate our mission at DeepMind is step one, solve intelligence, and then step two, use it to solve everything else. So we sort of think about the intelligence problem within this framework called reinforcement learning. And it's a very simple framework to describe. I'm just going to describe it with this simple diagram. So on the left-hand side here, you have the system itself, the AI system. And the AI system finds itself in some kind of environment that it's trying to achieve a goal in. And that environment could be real world or virtual. Now, the system only interacts with the environment in two ways. So firstly, it gets observations about the environment through its sensory apparatus. We normally use vision at DeepMind, but you could use other modalities. And these observations are always noisy and incomplete. So unlike the game of chess, the real world is actually very noisy and messy. And you never have full information about what's going on. And the job of the system is to build the best model of the world out there, statistical model of the world out there, based on these noisy observations. And once it has that model of the world, the second job of the system is to pick the best action that will get it closest towards its goal from the set of actions that are available to it at that moment in time. And once the system has decided which action that is, it outputs that action gets executed, it may or may not make some change to the environment, and that drives a new observation. And this whole system, although it's very simply described in this diagram, it has lots and lots of hidden complexities. And if we could solve everything behind this diagram, that would be enough for intelligence. So I'm just going to run this video now, this 1-minute video. This is Space Invaders, the most iconic game probably on Atari. And this first minute, this is before the first time the AI has ever seen this data stream. So don't forget, it doesn't know what it's playing, it doesn't know what it's controlling. And you can see it's actually losing its 3 lives. It's controlling the rocket here at the bottom of the screen. And it's losing its 3 lives immediately because it doesn't know what it's doing. But after you leave it playing overnight on a single GPU machine, you come back the next day, and now it's superhuman at the game. It's learned for itself through experience how to play. So you can see now every single shot it fires hits something. It can't be killed anymore. It's worked out that the pink mothership that comes across the top of the screen in a second is worth the most number of points. And it does these amazingly accurate shots to do that. And you can, if those of you remember Space Invaders, as there's less of them on the screen, they go faster. And just watch the last shot that it does, the rocket does. There's this predictive shot to hit the last Space Invader. So you can see how perfectly it sort of modeled the game world and that data stream. So accurately, it can predict ahead of time what is going to happen, just from the pixels on the screen. So this is the second video. It's my favorite video, actually. So this is a game of Breakout. And there's more gradations here of the agent getting better, the system getting better. So this is after 100 games. So just 100 games. And you can see, again here, the system is pretty terrible, but you can probably convince yourself that maybe it's starting to get the hang of the fact that it should move the bat towards the ball. Now this is after 300 games, so it's now hitting the ball back pretty consistently, and it's almost never missing, so it's about as good as the best humans can be at this game. And then we thought, that's pretty cool, but what would happen if we just left the machine playing the game for a couple more 100 games? And this amazing thing happened. What happened was it discovered the optimal strategy was to dig a tunnel around the left-hand side here and then send the ball, with this unbelievable accuracy round the back. So that's really cool because actually the brilliant programmers and researchers who are on this program, they're brilliant at programming and coming up with algorithms, but they're not so good at playing Atari. So they didn't actually know that strategy for themselves. So this is something that their own creation taught them. Games are kind of microcosm of the outside world. That's why games were invented. That's why humans find it fun to play. There's a rich history of computers tackling board games. It started with games like backgammon, drafts, and then finally there was Deep Blue in '97 that beat Kasparov at chess, which was obviously a huge watershed moment for game AI. Since then, the really big remaining sort of holy grail, if you like, has been Go. In chess, the number of possible moves is about 20 for the average position. In Go, it's about 200. Another way of viewing the complexity of Go is that the number of possible configurations of the board is more than the number of atoms in the universe. If you ask a great Go player why they played a particular move, sometimes they'll just tell you it felt right. So the one way you can think of it is that Go is a much more intuitive game,
whereas chess is a much more logic-based game. AlphaGo is our program to actually try and crack Go. We played the European champion Fan Wei in a 5-game match. We have an estimate of how strong a program is, but of course you never know. When you play a human player, they do all sorts of very interesting creative things that your programs don't necessarily do. So there's always an unknown.
When we play the first game, I lose. Interesting.
I think he was a bit stunned after the first game, and I think he was unsure as to whether he hadn't prepared enough or whether the program was really strong.
I think after first game, maybe he don't like fight. He like play slowly, so it's why begin the second game, I fight. Do mistakes sometimes. It's give me confidence. I think maybe I'm right. It's why for another game I fight all the time. This. Now it's complicated. But I lose all my game.
AlphaGo won 5-0, which is the first time ever a program has beaten a professional player. The way I see where we are now is that we've beaten the European champion now, and the next step for us is to try and challenge the legendary player Lee Sedol, who you can think of as the Roger Federer of Go. We always used to talk about, well, if we could eventually crack Go and have a program that could beat the world champion, then we must have invented some generic, general-purpose algorithm. So maybe we're on the cusp of all of that. And we're very excited about it, but it is just one rung on the ladder towards solving artificial intelligence.